All right, today's lecture is going to focus on looking at a few tidbits on wrapping up this concept of reaction rates with half-lives, integrated rate laws, talking a little bit about potential energy diagram, collision theory, a lot of just hodgepodge of different items to kind of wrap up a lot of kinetics. And then I'm going to introduce you into mechanisms, which is the last concept in this unit. All right, a half-life is defined as the amount of time it takes for half of the reactant to be consumed. So if you look over here at this chart that I've given you, if the initial concentration of A is 1 molar, okay, and the time of that would be, let's say this is being measured in seconds. So whenever we have a concentration of something at 0 seconds, we call that the initial concentration. So let's say the initial concentration of A is 1. The amount of time it takes to get from 1 molar down to 0.5. At 0.5, half of it has reacted, and let's say that takes 10 seconds. Okay? Then the next half-life would be how long it takes for it to go from 0.5 to 0.25, half of the remaining amount. You're going to see as we do half-lives, they start getting incrementally smaller and smaller, because theoretically, this graph, the concentration versus time graph, is never going to get to 0. We are never going to fully consume the reactants because of collisional aspects, which we'll talk about here in a few minutes. If you study the concentration versus time, if it takes another 10 seconds, or if it takes 20 seconds to go from 0.5 to 0.25 overall, we can see that it takes 10 seconds to go from 1 to 0.5. It takes another 10 seconds to go from 0.5 to 0.25. And let's say to get to 0.125, it takes a total of 30 seconds. But again, to go from 0.25 to 0.125, it takes another 10 seconds. Now, do half-lives always have to be consistent? In this problem, we would say that the half-life of this substance is 10 seconds. Every 10 seconds, half of the remaining reactant will be left. Every 10 seconds, half of it is left, and another half, and another half. Okay? If the half-lives are consistently spaced, where they're the same length of time, this is indicated that it's first order. So here's another proof for first order. If you are given a concentration or pressure versus time graph, you can see here this graph starts at 150. The half-life, or the time it takes to get to half of that pressure, is 75. Okay, so this amount of time, and when I drop it, this would be called the first half-life. Okay, and we can see here that this is about, let's say, 1,300 seconds. The second half-life will be the amount of time it takes to go from 75 to 37.5, or half of 75, which for this one now takes us to about a total of 2,600 seconds. We can see that the amount of time, the length of this segment, is exactly the same. Or, again, each half-life is looking like it's operating at 13,000 seconds. So if the half-lives are consistent, this indicates that the reaction is first order. On your green sheet, the third equation in the kinetic section is this one, in which the half-life of a first order reaction, and again, this equation only works for first order because their half-lives are consistently spaced. In this example problem, each half-life is 13,000 seconds. If we take 0.693, which is really the natural log of half, if we divide that by the rate constant, that gives me the half-life. Or, if I know the half-life, if I take 0.693 divided by the half-life, that gives me the rate constant. And again, I can only use this equation if it's first order. If it is not first order, I can't use this equation. Okay, so let's look at an example problem here. The reaction of CH3NC is first order. The figure above shows the concentration versus time graph. Or I should say, in this case, it's pressure versus time graph. Okay, that should say pressure. Okay, from the graph, estimate the half-life of the reaction. So we estimated, we've already done that, we estimated that the half-lives were at 13,000 seconds. And this was consistently 13,000 seconds. Each half-life was 13,000 seconds, which indicates it's first order. I have seen a national exam where they use this graph and they say, does the graph support that the reaction is first order? In this case, you would say yes, because the half-lives are consistently the same amount of time, 13,000 seconds. Okay, so now use the half-life to calculate the rate constant. Well, because it's first order, I can use the equation on the green sheet. So 13,000 seconds divided by, my fault, 0.693 divided by 13,000 seconds. All right, doing the math, I end up getting 5.33 times 10 to the negative fifth. And the units would have seconds on the bottom, so we would have inverse seconds. So this would be the half-life for this chemical reaction. And again, whenever you have first order reactants, the K, the rate constant, will have units of 1 over time, which is indicated by this chemical equation as well. 1 over seconds, because we're measuring time in seconds. Okay? So if you have a first order reaction, its half-lives are consistently evenly spaced with the same amount of time. If it's zeroth order, the half-lives get shorter and shorter. If it's second order, they get longer and longer. But again, these equations are not given to you in the green sheets, so do not worry about expecting to do those chemical equations on the national exam. All right, the next aspect is looking at temperature and how it affects the rate of reaction. Well, chemical reaction rates increase with temperature. The question becomes why? Why do they increase? Well, we know that the molecules move faster. If they move faster, there's going to be more collisions between the molecules, which can result in more successful collisions and therefore a faster chemical rate. The molecules also move faster, and therefore they hit harder, and if they hit harder, they are going to be able to react more successfully as well. If you remember back to writing rate laws before Christmas, to write a rate law, you write the word rate equals the rate constant times the concentration of the reactants raised to their orders. The rate constant K increases as temperature increases because the molecules collide more frequently, and therefore the rate constant has a greater value at higher temperatures. If the rate constant increases as the temperature goes up, that's going to now cause the rate of the reaction to go up because the rate constant is larger. So yes, if the temperature of the reaction goes up, the rate of the reaction goes up because the value of K gets bigger as well. Okay? Collision aspects. We've kind of already talked about this, but again, and just real quickly to review, in order for reactants to form products, they must collide with each other. So for example, if you have a reaction A plus B produces C, in order for this reaction to occur, a molecule of A must collide with a molecule of B. Okay? And there's a couple of requirements of this collision. First of all, it has to occur, but not all collisions will be successful. Okay, why is that? There are two requirements with collision theory. Okay? But one thing I do know is that if the temperature goes up, there are more collisions because the molecules are moving faster, and that's going to cause the rate of the reaction to increase. The first aspect to look at is the orientation of the collision. If you look at this example right here, you'll notice that in this reaction, the two green molecules strike each other, creating this molecule and this molecule. This is an effective collision because we are trying to create whatever this molecule is. Okay, I believe in this case in your textbook this is fluorine. We're creating the molecule F2 of fluorine gas from this chemical compound. Okay? In the second collision, the green molecule strikes the red particle, the red atom, and not the green one. And therefore, because it strikes there, it will not be able to form the molecule F2 because it doesn't collide with it, being able to rip it off from the original molecule. This would result in an unsuccessful collision because the collision doesn't occur in the right spot, the right location. So the first requirement in collision theory is the molecules have to strike in the correct orientation. If not, it will not be a successful collision. Okay? The second version theory is that they have to strike hard enough. Why do they have to strike hard enough? Because they have to strike with a minimal energy for the reaction to occur, because we have to break bonds in order to make new bonds. So if the collision is not hard enough, we will not have enough energy to break the bonds, and therefore the products cannot form. Again, we have to break the reactants apart in order to make the products. So here we see an example of a potential energy diagram. We're going to see them a lot on this next exam. So the starting point of this graph is the reactants. The ending point of this graph is products. And as we saw in the last unit, there ends up being this peak that results in this graph. The peak, at the top of the peak, is something called the activated complex. The activated complex is a substance that really doesn't exist in real life, but what it is, it's a compound in which it shows the possibility of new bonds forming and the old bonds breaking, or vice versa, the reactants reforming because there's not enough energy or the collision doesn't occur at the right spot to be able to form it. So we can see here is we've got a structure in which the molecule could go either way. We could make products or we could go back to reactants. Okay? In essence, the molecule is in a state of flux. It could go either way. Now, the activation energy is the amount of energy of the reactants to the peak. That is called the activation energy of the reaction. EA, a concept that you're going to want to get down very well for this exam, is called activation energy. The activation energy is the minimal amount of energy needed to break the bonds so that new bonds can be formed. This is called activation energy. So if the collision doesn't have the energy that is at this amount or greater, it cannot be a successful collision and products cannot form. Now, if the collision does hit hard enough, the collision still could be unsuccessful if the collision doesn't occur in the right position. So you got to be able to look at both variables have to be met in order for a successful collision to be met. One other thing, the difference in height of the reactants to the products. Here they say delta E. Actually, from our last unit, we called this delta H. The difference in height of the reactants to products tells me the enthalpy of this reaction. Real quickly looking at this reaction, would this be an example of an endothermic graph or exothermic? Hopefully you said exo, because the products are below the reactants, and therefore energy will be released, and we have a negative enthalpy value because energy is released into the surroundings because the products are more stable than the reactants. This is an example of an exothermic graph. Okay? All right, one last thing. This is a graph that you just saw too in the previous unit called Maxwell-Boltzmann. If you can remember back, which you should, it's only been a few weeks ago, At a higher temperature, this graph, the red line, shifts to the right. It gets wider and it gets shorter. But let's say the activation energy is 100 kilojoules. And let's say 100 kilojoules occurs right here. The blue section is the lower temperature graph. This shaded section right down here is defined as the number of collisions that meet or exceed the activation energy requirements. Okay? Only the collisions, only the number of collisions that are in this shaded region, these are the only collisions that theoretically could form products because they are going to be hitting hard enough. All of these other guys over here are not traveling fast enough, so the collisions between these two particles don't allow us to get over this hump of this hill, and therefore they will not have successful collisions. Okay? Also, not every single one of those collisions in that shaded region will occur and be successful because they might not hit in the right location either. So always realize that not all of those collisions will be successful as well. Now, what happens? At the higher temperature, you can see that now we add all this other region of space, this red section, so we get a larger number of collisions. At a higher temperature, there are more collisions that occur at or above the activation energy requirements. Therefore, there are more collisions occurring at higher energies, and therefore there are more chances of successful collisions. And this is why the rate of reactions increase as temperature increases. This right here is a explanation, a justification that I would severely write down and memorize, not only for this test, but for the national exam. They usually on the national exam will ask this key question: why does the rate of reaction increase as temperature goes up? You want to state this as your answer. At higher temperatures, the number of collisions that meet or exceed the activation energy requirement is increased. There are more collisions occurring at the necessary energy of activation. Therefore, there will be more chances of successful collisions. If there are more successful collisions, there are more, the rate of the reaction will be faster. So again, at higher temperatures, there are more collisions that are occurring at or above the energy of activation requirement for a successful collision. Since there are more of them occurring at this requirement, there will be more successful collisions and therefore a faster rate of reaction. That is a key concept to have down. All right, now down below, let's look at an example problem. Here you have 3 different graphs. Some of these graphs are endothermic, some are exothermic. These are all potential energy diagrams. What I'd like you to do right now is to pause the lecture, and I would like you to go ahead and identify the enthalpy and the activation energy for both the forward reaction and the reverse reaction for all 3 graphs. Okay, please do that now. All right, looking in the first reaction, if we're looking at the forward reaction, the reaction would go in this way. So this would be the reactants and this would be the products. So the activation energy, again, is the height from the reactants up to the peak, which is given as 15 kilojoules. The enthalpy of the reaction then is the difference between the reactants and the products, which is -10. Now, the reverse reaction would be looking at going the reaction in the opposite. So now the products are the reactants, and the reactants are the products. So now I'm going to look at the reaction going from right to left. Now, to go from the reactants all the way up to the products, it's 10 to the dash line and it's another 15 to the peak. So in the reverse reaction, it's a total of 25 kilojoules from the reactants all the way up to the peak. The difference between the products and the reactants is still the same, but now it's opposite. If you think back to the previous unit, if it's endothermic in one direction, it's exothermic in the other direction. Okay? So for this one, it's negative 10 forward, it's positive 10 in the reverse. Okay? Number 2, it was 25 up to the peak for the activation energy, and it was negative 15 for the enthalpy. The reverse direction, again, the enthalpy will be the same, but will be opposite in sign. But the activation energy for the reverse reaction will be now from the reactants up to the peak going right to left, which would be a total of 40 kilojoules. And lastly, number 3, going forward, it's 20 kilojoules to the peak, and it's positive 5. This is the only endothermic graph going forward. In the reverse direction, now I'm going from the reactants to the peak, which is not 25 here because we're starting 5 above. It's actually 15 kilojoules going from the reactants now, okay, up to the peak in the reverse direction. And positive 5 becomes now negative 5. In the reverse direction, the endothermic becomes the exothermic graph. Letter A says, assume all 3 reactions have nearly the same frequency factors. Rank the reactions from slowest to fastest. Well, what would I want to look at? And we're looking at the forward reactions here, just the forward ones. How would I figure out who's going to be the fastest and who's going to be the slowest? Am I going to look at the activation energy or the enthalpy of the reaction? To do this, we want to look at activation energy. Because it's the activation energy, how many of these collisions are occurring at the necessary activation energy requirements? Okay? So with that, if we're looking at that in this problem, the first reaction's got 15, the second one's got 25, and the last one's got 20. The one with the lowest activation energy will be the one that will have the most possible collisions because it has the least energy requirements. So reaction 1 will be the fastest and reaction 2 will be the slowest. So in order of slowest to fastest, 2 is the slowest because it has the highest energy of activation. Then comes number 3. And then the fastest reaction will be number 1 because it has the lowest energy of activation requirements. The less energy that's required, the more likely it's going to have a potential successful collision. Okay, so those are some of the key points on potential energy diagrams and how to figure out both the activation energy and the enthalpy of the reaction. I also want to real briefly talk about reaction mechanisms because that's going to be the last concept in this unit that we're going to focus in on. I want to introduce it. A mechanism, in essence, is a pathway. How the reaction gets from reactants to products. What process does it endure? So for example, let's say we have a reaction. 2A reacts with B to produce a C and 2D. If in the national exam they tell you the reaction is elementary, if you see the word elementary reaction, that tells you the reaction occurs in a single event. What that means on a potential energy diagram is that you are going to have one hump. If on the potential energy diagram you see one hump, that means it occurs in one step, and that tells you that it's an elementary reaction. What does that mean? Why do they say elementary? How the reaction is written is how it occurs. So for this reaction right here, two A molecules and one B molecule bash into each other with enough energy and at the right spot for it to successfully form products. Three molecules are involved in the collision, two A's and a B. This is called a termolecular equation. Termolecular means three molecules are colliding to form the products. This tends to be quite rare and very uncommon because the likelihood of three molecules colliding at the right spot with enough energy is fairly low. Unimolecular is where there's only one molecule involved in a collision. It theoretically could just hit off of a wall, and because it hits hard enough, it could jostle and make new products, or potentially more likely decompose into something else. Or it could bump into itself and not react with itself, but hit with itself hard enough that it would also break and form new bonds as well. Bimolecular is where two molecules collide with each other, as you can see here. One molecule of NO collides with one molecule of N2 to form the products. Okay, bimolecular means two molecules collide to form the products. The other possibility is something called a multiple step mechanism. If it's a multiple step mechanism, the reaction occurs in a set of steps. Here you can see a potential energy diagram that has two humps. If it has two humps, that means it occurs in two steps. Each step has a chemical rate of reaction, and we'll talk more about rates next week when we get into that. But for right now, two humps means that it occurs in two steps. So if you look at this reaction, the overall equation is NO2 plus CO produces NO and CO2. In this mechanism, it occurs in two steps. First of all, NO2 and NO2 will collide with each other, forming NO3 and NO. Then the NO3 that is developed will collide with NCO to produce NO2 and CO2. All right, I quickly wrote down the steps of the equation and I rewrote them down. And if you add the two equations together, again, we're applying Hess's law here, there's an NO2 on the left and two on the, one on the right and two on the left. So one of them cancels, and NO3 also cancels. What I get done with when I'm done is the overall equation ends up adding to the desired equation. So this mechanism is viable. The steps of the mechanism add up to the overall equation. And therefore, we can see, in this case, that two humps result. Okay, a question they might ask on the national exam is, which step is the slowest step? Is step 1 right here the slowest step, or is step 2 the slowest step? What do you think? If you say step 1, you are correct. Why is step 1 the slowest step? It has the greatest activation energy requirement. The activation energy has to go all the way from the reactants up to the first peak. That would be the activation energy for step 1. The activation energy for step 2 would now be the height of the next starting spot, the mid spot, that bottom gap of the two humps, up to the next peak. This right here would be the activation energy for step 2. You can see that the amount of energy it takes to meet the first hump is much bigger than the second hump. So there's a lot more reactions that can be successful if there's a lower energy requirement. So the higher the activation energy, the slower that step is, because there's less molecules that can meet that energy requirement. One other thing that might pop up is something called an intermediate. An intermediate is a substance that is formed in the chemical equation, but then is consumed, and it ends up not being in this overall equation. If you look at this reaction that I just drew for you, you'll notice that the chemical compound NO3 is made in the first step. However, in the next step, it is consumed, and therefore it is not part of the overall equation. This is what is called an intermediate. An intermediate can be found in between the humps because it is a compound that is formed and then consumed, but ends up not being part of the overall equation. So in this reaction, NO3 would be called the intermediate. All right, so let's go ahead and apply what we just learned with mechanisms. And let's go ahead and see, I'm going to pause the lecture right now and see if you can go ahead and utilize this information to answer the questions with letter C. All right, step 1 is called unimolecular because you'll notice that only one molecule is involved in the first step, which means one molecule will collide with something, maybe the walls of the container, and it will react. Step 2 is bimolecular because there's two molecules, an ozone and an oxygen atom will collide. Therefore, it's bimolecular because there's two particles involved in the collision. If I sum up the two steps, you'll notice that the O cancels. We're left with two ozones on the left and three oxygens on the right. And here is the overall equation of ozone becoming oxygen. And the intermediate is O because it's formed in step 1 and then consumed in step 2. It's in the mechanism but is not in the overall equation that we just found out. So therefore, the O would be called an intermediate. Okay? So again, an elementary reaction is one in which how the reaction is written is exactly how the reaction occurs, and the potential energy diagram will show one hump. If it's a multiple step mechanism, each step will add up to all the steps will add up to the overall equation, and the step that has the greatest activation energy jump will be the slowest step of the two. The requirement of the mechanism is that the steps of the mechanism will add to the overall equation. And in between the steps, you can form something called an intermediate. An intermediate is a chemical compound that's formed and then later consumed, but is not a reactant or product in the overall equation. Okay, those are some key points and concepts. If you have any questions on any of this material, don't be afraid to ask. Again, thanks for listening.